Good afternoon. Uh, let's recall the formula for calculating volumes. We slice a solid into slices like salamis, and A of x is the cross sections as we slice it open. Then a small slice, the volume is going to be the cross-sectional area times dx, and then the entire volume therefore is a sum of all the slices, the volume of the slices, and the sum of ax dx. Then apply fundamental theorem of calculus, let dx go to 0, and the summation sign turns into the integral sign on one end to the other. We apply these to the triangular problem spinning around axis. I take over here the red triangle, we're going to spin around the vertical axis like this, and we get then these shapes. And if the triangle is situated in this manner, then we get bowl shapes. And the triangle can also spin around a horizontal axis and forming basically the same shapes. Let's look at these two cases because around the spinning around the x-axis. And let's suppose this is the x-axis, and we go from A to B, and this is x equal to A, x equal to B, and we do the spinning. And if we slice vertically across the axis with spinning, in this case the x-axis, okay, we will get rings, and the area of rings is very simple. It's pi big R squared minus pi little r squared, take the pi out, and that's the cross-section area. Therefore, the volume is going to be the integral of the cross-section area. Here's a formula, and here's an example. Okay, and we have these red templates revolving around a horizontal axis as x goes from 0 to 3. So if I at a point x vertically, I track how big the ring, the big R is. So big R is from here all the way to 2, minus 2. So it's 2x, the height of the y, the top part, plus the 2, or minus 2. And of course, the little r stays as 2 all the way across. And so this is the volume for these particular solids. And here is the Gaussian methods. If I do it, if the things is rotating around vertically around the y-axis now, okay. Now the ring is formed by a y, given y, we take the horizontal cross sections, and then we get the rings. So these are the formulas you will use, and out of y will be the x position, the x coordinate, okay, of the point, or the distance, the x distance of that point. So, but it needs to be expressed in y. Here's a cylindrical method. Okay, against here's against the x-axis. Okay, we rotate this shape around the x-axis, and then we get a cylinder. And the cylinders, the area of the cylinders, surface area of the cylinder is going to be 2 pi r. 2 pi r, of course, is the circumference, and times the height of the cylinder, in this case, the width of the band. And so everything now in this case is expressed in y, because we get a cylinder by taking a y cross sections like these. Y is equal to some numbers, and therefore it's the integral set up using y. Okay, for instance, like this case, use cylindrical method set up this integral. First of all, I get cylinders y, take y equal to a constant and follow it as it revolves around y equal to minus 2. of course, then it forms a cylinder in this case. And to calculate the surface area of the cylinders, first I have to figure out what's the radius. So a radius is from y, of course, to y minus 2. And then the height is a difference in the x coordinate. Here is 3, so x must be 3/2 over here, and here is by the function, the x coordinate is y over 2, therefore you subtract them, and then surface area of that cylinder is 2 pi RH, and put that as the integrand, and that's it. Okay, and here is the formula for the horizontal case, but using the cylindrical methods. This is the case one more time of rotating the integral along x-axis. Okay, and rotating around the y-axis. And that's it. Bye-bye.